Let me take you through a well-known algorithm created by Hans-Peter Luhn that was used to validate credit card numbers. The algorithm is often used to validate credit card numbers, but it can verify any number really. It relies on generating a check digit, which is derived from the number itself and put at the end. It's used mostly when validating user input. If any one of the numbers is typed incorrectly, it will detect it and fail the validation. It works like this. Given we have the full number and the checksum, to verify it's valid, we do the following. Starting from the rightmost digit, we double every second digit. If the product of this multiplication is greater than 9, like 16 and 18 in our example, we add the two digits together, so we get 7 and 9. We'll take the rest of the digits down, and then sum them all together. If that result is exactly divisible by 10, it's valid. So that's the basic algorithm. Let's have a look at a traditional imperative implementation. And this one's in Java. So to do the doubling part, we traverse backwards from the end and keep a temporary variable around to work out if we're on the second digit or not. At the end of the loop, we toggle this. During the traversal, we turn the character to an int, and if the isSecond flag says so, we double it. We're keeping a running sum here, and in this bit, we add to it, taking care of whether the product is a double digit or not. We use integer division and modulo division to get the remainder. When we exit the loop, having modified the sum variable as we went, we can use modulo again to check if it's exactly divisible by 10. What do you think of the implementation? Before we discuss it, let's look at how we might do this in Scala by chaining transformations in a functional style. So in Scala, we'll follow the same general approach, but we'll describe the algorithm instead as a pipeline of computations, transforming data as we go. It's probably easier to work with numbers than the input string, so we'll turn the string into a list of numbers. We'll use map to transform each character in the string to a digit, which is really an int. Then rather than enumerate these in a for loop backwards, we'll just reverse the list so we can process them normally and use conventional methods. The next step is to double every second digit, but in a functional style we don't want to keep any variables around to manage the state. Instead we'll do another transformation to add some extra information into the list so we can tell its original position. We'll use a function called zipWithIndex. It takes a collection and turns it into a collection of tuples containing the original value and its index. This will transform our list of digits into a list of tuples, which we have the value and the value's position or index. And we'll use this in the next step. As we continue to transform, this time with the map function, we'll check if that index we just created is odd or even, and use it as a way to find every second value. We can use some special syntax here and a partial function to unapply the tuple to make it easier to get at. So now we have access to the index, we can check if it's even. If so, return the digit, otherwise double the digit. Done. We've mapped our list of tuples back into a list of ints at this point, with every other number being doubled. We now have a list of digits ready to sum, almost. Some of these numbers may be greater than 9, and these digits need to be added together before we can sum the lot. Have you spotted this is the perfect excuse for a flat map? We're going to turn a list of one number into a list of two numbers. So the flat map takes a function that creates a list with two values, the first the integer division, the second the modulo division. If any of these end up as 0, we could remove them with the filter, but that's kind of an optimization, so I'll leave that off, even though it's a good example of a pipeline within a pipeline. The last computation is to sum all the elements. We'll transform a list of numbers into a single number using the inbuilt sum function. Given the result of this, we can just check if it's divisible by 10 exactly to infer if it's a valid number or not. And you should be able to see that this one is valid and this one is not. Yep, great. Okay, so we've seen two versions of the same thing, one imperative and one in a more functional style. But to really find out what makes both tick, we really need to look at them side by side. So let's have a look at both of them together. What do you think? Certainly they could both do with some refactoring. We could pull out those calculations and give them friendlier names. But what else? There's a lot of temporary variables in the imperative one. Temporary variables tend to lead to longer methods. By their nature, they rely on side effects, and you can see sum is modified in various places, an easy way for subtle bugs to sneak in. In the functional style, we don't have any temporary variables. We rely on transformation to prepare the set of numbers and then do the final computation of the sum using the sum method. This is handy, but also meant we had to think about things slightly differently. We broke the problem down into a sequence of small steps. We didn't try and solve it all in one go. When we got to the problem of doubling every second number, we resolved it by transforming the data in such a way that we had the information that we'd need. We retained the digit's position in the list. The same when we came to filtering out zeros. We could make small localized decisions that we knew would affect the next step in the transformation. When we look at the imperative version, the responsibilities for the different parts of the algorithm are spread all over the place. The toggle for is_second is set at the top, used in the middle, and toggled at the end. This can be hard to track if the method were much longer. The sum is a running total, and to see how the sum is affected, we have to look at the method in its entirety. Functional style version has small discrete steps, which can be easily understood in isolation, and arguably can be read and understood more readily because they progress logically from left to right. As I mentioned, the imperative style relies on mutation via side effects. The functional style has no mutation. It works against immutable lists. We haven't really tried to deal with any errors in this, by the way. If a non-numeric were to be passed in, both versions would blow up. I'm sure you can picture how messy things will get if we add exception handling into the imperative version. We'd be conflating non-functional concerns with the algorithm, which could lead to potentially more bugs and certainly harder to read code. When we think of things like transformation of data, we can imagine a transformation being into a richer type that can represent error conditions as well as the happy path. That might sound a bit theoretical, but in practice, it becomes fairly trivial to tag on exception handling to the existing implementation with types like either or try, and it will retain the same sequence of steps just with richer transformations. My final observation is more about declarative styles than pipelining like this. Because we delegate processing to functions of the list in the functional style, it's easier to vary how they go about their business. So for example, if you wanted to handle lists of infinite size, a bit silly in this example, or process things in parallel, you wouldn't need to change the implementation, those sequence of steps, only the types. Whereas in the imperative version, you're explicitly choosing the mechanism, and for example, modifying it to work in parallel would be a non-trivial task